Okay, so let's do a problem with a uniform body, but in 2D. So we're looking at a half uniform disk with radius r, and the density of the disk is sigma. So that sigma is kilograms per square meter. So it's mass per area compared to mass per length in the in 1D. So we have this object here, and before we do any calculation, we should use our symmetry argument to see where the center of mass should lie. So since this system has a symmetry axis, left and right are mirror image of each other. So we can imagine the center mass lies along this line here, the center line. So let me move this this shape to to line up with a grid line. Okay, something like this, so that I have the center line here. I can easily draw a line across there. Okay. All right. So the center mass should be along this line. Let's call this y, and we'll also set up an x-axis. I'll call this x, and here's the origin. All right, so the center mass is somewhere over here, and we need to find out where. And in order to do this calculation, let's draw an arbitrary slice. Let's slice up the this half disk. So we'll take a slice. See, that's a small slice, and we can imagine just keep slicing. So the half disk will be in slices, and we can stack the slices together to basically to make this half disk. So about this slice, the vertical position is roughly the center of that slice. So we have that vertical height is y, and the width of the slice, let's call that L. This L here. And this L depends on y. So if you're slicing a little further down here, you'll be getting a wider slice. So the L will increase as y decreases. And the opposite will happen if you have a higher y coordinate. Say if you're sliding over here, then your width is narrower. Okay, so that probably needs to be figured out. And we also have this equal to r, right? This is radius. This is also equal to r. And we can also draw a line here between this arbitrary slice and the origin. So let me line this up before I draw it. It's a digital pen. Okay, roughly right. So this is also a radius r. So there are many different places you can have this r here. And in this right angle triangle, we have this, that, and that. So in this right angle triangle, we can calculate L's, well, not L, half L, right? Half of L, which is this side. And half of L squared plus y squared is equal to r squared according to Pythagorean theorem. So we can find out L over 2. So this side squared is equal to hypotenuse squared minus the other side squared. Or you can get L over 2, which is equal to square root of r squared minus y squared. And then L, let's move it down. And then L is equal to the square root twice the square root of r squared minus y squared. Okay, so now we figured out L. That is an important parameter to figure out. So let's get back to this this slice here, or maybe a just a bar. Okay, so this slice here should have a mass of delta m. Okay, so how much mass did I slice out of this half disk? Well, that depends on the area of the slice, because the whole disk has an area, and it has a total mass, some value, and the density is uniform. So the area times density should produce the mass of the slice. So that is supposed to be equal to area times density. The density is uniform. Okay, so what is the area then? Well, if you look carefully, these sides are actually curves. Even if you can imagine these are straight lines, this is a trapezoid, right? So the top and bottom are slightly different in width, but we want to approximate this as a rectangle. So the width is just L, regardless of top or bottom. So we're stacking a bunch of slices that are thin rectangles. So we just approximate. So now we have approximate area, which is a rectangle area. So the rectangle's width is L, and its height is this thickness, because this axis is y-axis. So the thickness, the small amount in that axis, will be called delta y. So we use that over here. So width times height, so that's the area, approximate area, and times the density. So the approximation will become exact if you take delta y limit to 0, right? So let's write that out. So the limit of delta m when delta y is pushed towards 0 now is equal to dm, infinitesimally small mass, and then the other side delta y becomes dy, so sigma L dy, and substitute the L with this expression, and there's a 2 sigma square root r squared minus y squared times dy is equal to dm. So this is the important relationship we just found out, how to turn the mass into coordinates, because we have dm in our integrals, and if we cannot turn dm into something that we can integrate, such as y, then the integral cannot be calculated. So now we have this relationship, we can move on. So the first thing we need to integrate is this, dm. Right, so let's put a formula here to remind us we're getting y center mass. And here we have y dm over just dm. Right, so y dm, let's calculate that later. So dm, and what is this thing? This is expected to be the mass total. So let's use a quick trick here. Instead of doing the integration, which we could demonstrate later, we'll just say that we have the total mass here, which is supposed to be the total area times the density. So the total area, half a disk, so pi r squared over 2, half a disk, and times the density. So this is our total mass, the bottom of this expression. So exactly how we do it, that takes actually more steps than doing the top, interestingly. So let's do the top. So the top is y dm. We substitute this dm with this expression. So 2 sigma y square root r squared minus y squared dy. Now let's specify the limits here. So y start from 0, you start stacking from the bottom all the way up to the r value of y. So there you go. And okay, how do we do this problem? Well, if you know integral calculus enough, you should be able to spot how to do it. But let's assume that you only have very basic understanding of integral being the inverse of derivatives. So let's do it slowly. And we have the 2r here. I'll move the not 2r, 2y here. We'll move it over to the other side of the square root. So we have a 2y dy. Okay. So we know that dy squared, y squared, or dy is what? Is 2y, right? So if we multiply both sides of this equation by dy, so this whole thing times dy, then well, the left side will no longer have dy on the denominator. The right side will have dy. So d of y squared is equal to 2y dy. Alright, so we have 2y dy here, and we also have it here. And then we can replace that with this. So the dummy variable has turned from y into y squared. That works fine with us because this is a y squared. That is a dummy variable, not a dummy variable squared anymore, if you assume y squared to be your dummy variable. So let's continue on. Now we have r squared minus y squared d of y squared. If you're not comfortable looking at this, let's do something else. Let's define a equals y squared. Okay, so let's have that. So now our integration turns into a. Alright, so let's keep saying what we have before here. Okay, minus a square root of dA. Okay, so let's do some explanations on the right side. So okay, what about d minus a over dA? That is minus 1, right? So we know that then d of minus a is negative of dA. Okay, that makes sense. A negative increment is negative of the positive increment. Okay, so using that, we can actually turn this into a negative d of negative a. We just have to put a negative in front. And what happens with this? Okay, so d r squared minus a. Okay, we know that r squared is a constant, doesn't change with a. Well, now we have this dr squared over dA. And we also have this d of negative a. We can actually just move that past the d or dA. Right, r squared is a constant of a, so this is a 0. That's a 0. And here we have a negative 1. So what I just proved was that d of r squared minus a is equal to minus dA. Okay, so what's the use of that? Well, I can say that instead of using a as dummy variable, I can transition into r squared minus a. So this whole thing in the square root is one dummy variable. So let me do another substitution here. So let's assume that we discard a, we just say now we have b. b is equal to r squared minus a. So how does our integral look like under this substitution? Y dm equals, so now we have the whole thing b under square root, so b to the 1/2 power. And okay, dA. Remember, dA's negative is the same as dB, right? So we can continue to write this on the right side. This is actually dB. This is b is equal to negative dA. Okay, so if I had a dA, I'll just say it's negative dB or negative b. And I can factor out negative. So b to the 1/2 power dB. And this is just like any other antiderivative where you have a power of a variable. And you can imagine, so what kind of a function when you take derivative will become 1/2 power, and you must have started with 3/2 powers, right? So let's keep writing things on the right side. So if you have a dv 3/2 power over dv, you'll have you pull out this factor, all right, 3/2, and then you decrement that from 3/2 to 3/2 minus 1/2. Okay, so that's how you can get b. So what this means is if you just want this, you multiply by 2, divide by 3, so 2, 3, right? So basically this function here differentiates into this. So if you integrate, you get this function back. So that's where we get this function back, a negative 2/3 b 3/2. Okay, and we need to put in the limits. Okay, so let's trace back where the b is, where the a is. Okay, so our original limit was the y, right? So the y limit, the y disappeared when I substituted this in, so the y disappeared. So let's put this here as y equals 0 to y equals to r, right? So the whole stack of these slices. So this limit should be corresponding to when y is equal to 0. So let's see, when y is equal to 0, then a is equal to 0. And then when a is equal to 0, b is equal to r squared. Okay, so this limit is r squared. And then the next one is y equals to r. Okay, then a equals r squared. And then b equals r squared minus r squared is equal to 0. So that's our limit. And we can pretty much ignore that. When you plug it in, it gets 0. And this has a negative that cancels that other negative. So now we have 2/3, this b gets substituted with r squared reaching the power of 3/2. So if you're forgetting about how to do these powers, this is how to do it. So 2 times 3/2, so those two will divide out and you have that, right, the third power. Okay, so let's see, I think we're missing a sigma here. That's okay, we'll add a sigma back, and we'll have the sigma here, we'll have the sigma here, we'll also have sigma here, and sigma here. So we have 2 sigma r cubed over 3. And then we make a fraction, right? So the y center of mass is equal to the fraction of this over that. So 2 sigma r cubed over 3 divided by pi r squared sigma over 2. Okay, so numerators, okay, divide out, r squared is gone, and then r cubed becomes just r. Okay, so now we still have a few values left. We have this on the top, that's the bottom of the bottom, so flip out to the top, and then you have a 4. And these two denominators, you have 3 pi, so 4 over 3 pi, that's almost 4 over 9. Okay. And then you also have this r here. And interestingly enough, the density doesn't matter, right? And it's only dependent on the geometry, the geometric shape. Thank you.